All right. So what was it that Thomson discovered about the atom? Okay. He anything else? No. Yeah, but the plum pudding model isn't what the atom is. What did he discover about the atom that is still true? There's a positive charge and a negative charge, and the negative charge can come off. And that's our electron. Okay with that? The rest of it was incorrect. But he definitely knew there was a negative charge, he knew there was a positive charge, and he knew one of them came off, and that was a negative charge, is what he called it. How about Rutherford? You okay with that? He didn't discover it was positively charged. He verified that it was positively charged, but we already knew it was positively charged, right? Because Thomson had figured that out. He knew that the thing that came off was negative, so the thing that was left behind had to be positive because when they came together, they had no overall charge. So they must be canceling themselves out when they were connected. So he knew that the thing that was left behind had to be positive, but the question was it dense or was it not dense? And they figured out that it was really tiny and it was very, very dense. Okay with that? What did he not discover? No neutron, anything else? He didn't discover the proton. He just figured out where the protons were located. He knew where they were, but didn't know what the nucleus consisted of. I should probably write dense here. Soddy, what's Soddy's discovery? Yeah. Chadwick? Okay. Isotope? What do we got there? There's two ways you could answer this question. You could talk about one thing by itself as an isotope, or you can talk about two things related to each other as an isotope. So if it was one thing, what are we talking about? If we're talking about one thing, it's just an element, or we okay with that? It's an element with a set number of neutrons. So hydrogen 2 is what? One hydrogen, or hydrogen with its one proton, because it's hydrogen, and then one neutron. And that isn't a particular isotope of an atom. Or I could relate it to another isotope of hydrogen, which would be, say, hydrogen 1 or hydrogen 3. So it's either you talk about it as one thing, like an element with a set number of neutrons, or two atoms of same element. What else? With different numbers of neutrons. Okay. Allotrope? Which one was that? Oh, wait, I forgot to give an example up here. We'll go with hydrogen 1 and hydrogen 3. Sorry, say that again?
It's atoms with multiple forms based on the structure. So like,
How about atoms of the same element?
yeah.
And best examples are like graphite and diamond. And charcoal. And buckyball.
Buckyball is a structure of carbon or is other stuff to it.
No.
Why is that? Like
Why carbon?
what?
Why carbon?
Well, like graphite goes with pencils. Diamonds are really expensive. Buckyballs are used for just being buckyballs. Got it.
There's an idea that we might be able to use it as a drug delivery method. Put a drug inside the buckyball, send drug out. We're not really sure how to open it up once it gets to where it's supposed to be. Or you can use it as a lubricant. And people use graphite as a lubricant because it's dry, but it's also pretty damn messy. All that dust gets all over the place. Same situation with this. So the graphite, why does the graphite act like a good lubricant for like a... Yeah, those pieces are very structurally sound this way, but they're not structurally sound this way. So they just slip over the top of each other. And the buckyballs are basically like tiny little ball bearings that I put in there, and so everything just rolls over the top. They're just more expensive, but probably be seen. I mean, there are people that are trying to use it as a lubricant for like things that spin, axles and whatnot, but they seem to break down under the temperature, higher temperatures, so we'll see what happens with it. Diatomic.
Atoms that always compares.
How do you the same element always comes first?
Atoms at normal pressure and temperature. H2, N2, there's 7 of them total. So the implication is if you're given a question and you see something like chlorine gas is being used, and when you go to write the chemical formula, what do you need to write? Cl2, because it's not ever Cl, if it's the element. Why 33 years on that neutron?
You're not looking for it.
Nobody looking. And
the people in charge didn't really care about it.
no, I wouldn't say
Wait for them to die.
has no charge. Has no charge. So hard to interact with. All right, so I got some beryllium here, and beryllium's atomic number is what? 4. So 4 for the atomic number means what? There are 4 protons. And since this is an atom, what else do I know? And it's beryllium. And so I've got something with 82 for its proton number, so I got 82 for its electron number, and anything with 82 protons is what? Pb. And then if this particular lead has a total mass of 207, then what's the number of neutrons? So 125, is that right? Yeah, 125. And I got myself some osmium, so if I'm looking at element osmium, what do I know? 66? 76. So this guy has 76 protons, so he's got 76 neutrons. And if this particular isotope of osmium has a total mass of 190, then it has 124? 114. 114 total neutrons. And if I'm looking at an element named radium, then it's Ra for its symbol, and it's 88 for its atomic number, which means it's 88 for its electron number. And if I add the 88 and the 133 together, I get wait, what'd you say? Don't say point. Why not? This is an atom, and that number up there is what?
Oh, an average.
Averages of a bunch of different atoms. So this number right here, always going to be what? Always going to be a whole number, because we're talking about one particular atom. So these guys will always be whole number. We didn't get to this, but oh no, we got to this. It was the other class we didn't get to. So what's the shape based on? Reactivity. That's it. Chemical reactivity.